Welcome to the first video of topic 1. Today we're going to be going over combinatorics. And combinatorics is a really important branch of mathematics that is central to a lot of probability and statistics that you deal with in year 11 and year 12, and also if you extend into probability and statistics study at university, which I think is important to a lot of university courses. Combinatorics is really central. So these are the SCASA bullet points for the concepts within combinatorics that you need to know for year 11 methods. So I'll be going over understanding the notion of what a combination is, using notation to represent combinations. There are a couple of different ways you can represent combinations, and then going over some geometric properties of combinations that allow Pascal's triangle, for example, to have the properties that it does. So I'll go over the first point first. Now I'll just turn my camera off so I can start writing on each of the slides to explain the concepts.
Okay, so first of all, what we want to do is we want to define what a combination is. What a combination is, most broadly, is its a counting technique. What do I mean by counting technique? By counting technique, I mean that a combination is a way of counting things in a more efficient way than we would normally. So, this is an example of where we would use combinations. Let's say we have 5 people, and out of these 5 people, we need to choose 2 of them. Let's say, for example, maybe we have 5 equally qualified job candidates and we don't have a preference, but we have 2 job positions to fill. Or let's say we have 5 people we need to select for a sports team. One way we could figure out all the different ways that we could fill up those 2 positions is by counting every single possibility. So we could have these 2 people, we could have these 2 people, these 2 people, these 2 people. That's 4 different ways of filling up those 2 positions. So 1, 2, 3, 4. We could have 5, 6, 7, 8, 9, 10. Okay, so that gives us 10 different ways. A faster way of representing all the different ways we can fill up those 2 positions is our 5 people and choosing 2 of those people. This is what a combination is. And we'll get to what a combination is defined as and why it's faster in the next slide. Okay, so we were looking at our case of 5 people and we got our 5 choose 2. This was one notation for combinations. Another way we can represent combinations is in this way. If we want to generalize this more broadly, we can write the combination as n choose r. If you remember, the 5 was the number of objects we were choosing from, and the 2 was the number of objects we had to choose. So more broadly, if we write combinations like this as well, we can write combinations as n being the number of objects we need to choose from. Sorry, I'll change that color so it's consistent. There we go. The number of objects, the number of objects to choose from, and r is the number of objects we have to choose. Okay. So now we've come to a definition of what a combination is intuitively. We want to know what it is mathematically, what it's equal to mathematically. A combination of n choose r is going to be equal to n factorial divided by r factorial n minus r factorial. Now this is a new notation you might see. Factorial. What does factorial mean, this exclamation mark? Let's give an example to illustrate. 5 factorial is equal to 5 times 4 times 3 times 2 times 1. Similarly, 4 factorial is equal to 4 times 3 times 2 times 1. So a factorial is defined as the number times each consecutive decreasing number. You'll notice that these numbers are the same as these numbers. Okay, so we can write 5 factorial as 5 times 4 factorial. This here is referred to as the recursive property of combinations. If we wanted to generalize our factorial definition to n factorial, that's going to be equal to n times n minus 1 times n minus 2 times etc. You don't need to exactly understand why this definition works. It's just enough to be able to apply it. The reason why is because understanding this definition hinges on understanding of permutations. If you do want to have a look at what permutations are and then how combinations are defined in a more conceptual sense, then you can check out my video on combinations and permutations in the specialist course, the Year 11 specialist course. That'll be uploaded a little bit later. Okay, so let's give an example of how we might use a combination. Let's have a look at our 5 choose 2 example, and I'm going to adopt this notation here. 5 choose 2 is equal to 5 factorial divided by 2 factorial times 5 minus 2 factorial, which I can write as 5 factorial divided by 2 factorial times 3 factorial. Note that I can write my 5 factorial as 5 times 4 times 3 factorial. 2 factorial, 3 factorial. So that's a times between those, in case that isn't clear. Okay, so I can cancel these two out. And the reason why is because that's 3 times 2 times 1 over 3 times 2 times 1. And so those two are equal. And so as a result, we have 5 times 4 over 2 times 1, which is equal to 20 divided by 2, which is equal to 10. Okay. Let's take a look at Pascal's triangle. So that's this point, 1.1.3. Okay, so Pascal's triangle is this. This is probably something you'll have seen pinned to math boards because it really is a central concept in math. And it goes on and so forth. Some of the properties I'm just going to point out right off the bat are that it's symmetric about the vertical line and that each entry is equal to the sum of the two entries directly above it. And you can see that, so on and so forth. What Pascal's triangle actually is it's a pyramid of combinations. The very first entry is 0, choose 0, and that corresponds to this one. That makes sense, because you've got 0 objects and you're trying to choose 0 objects from those 0 objects. There's only one way of doing that. The next row, we move to n equals 1. 1 choose 0, 1 choose 1. Again, one way of choosing no objects from 0 objects, and one way of choosing one object from one object. 2 choose 0, 2 choose 1, 2 choose 2, 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. You'll notice I referred to this row as the n equals 1 row. That's because this top value here is n equals 1. And notationally, we refer to Pascal's triangle in this way. This is row n equals 0, n equals 1, n equals 2, n equals 3, and so on and so forth. Okay, it's important to distinguish as well that this n equals 0 is the first row, this n equals 1 is the second row, n equals 2 is the third row, and n equals 3 is the fourth row. That might be a little bit confusing, but this is the notation that we would most normally use when we were referring to the rows, rather than this. So, let's say we want to figure out the n equals 6 row. That'll be 6 choose 0, 6 choose 1, 6 choose 2, 6 choose 3, 6 choose 4, 6 choose 5, and 6 choose 6. Okay? And we can evaluate each of these numbers. There's one way of choosing 0 objects from 6 objects, so 1. 6 ways here. Let me try to remember what this one was. 15, 20, 15, 6, and 1. Okay, now I pointed out two distinct properties. The first property I pointed out was that each entry was equal to the sum of the entries directly above it. If I write this in combination notation, that's this. Oh, sorry. N choose R equals n minus 1 choose R minus 1 plus n minus 1 choose R. Let's give an example. Let's look at 3 choose 1. 3 choose 1. That's going to be equal to 3 minus 1 is 2, choose 1 minus 1 is 0, plus 3 minus 1 is 2, choose R, 1. 2 choose 0, 2 choose 1. Exactly as expected. This is one important property of combinations. Another important property I noticed is the fact that it's symmetrical about the vertical axis. The way we can represent this with combinations is that n choose R is equal to n choose n minus R. So this object is equal to this object. And if we look at our numbers over here in this table, we can see that's true as well. This is 1, this is 3 minus 1. This is 0, this is 3 minus 0. We can also come to an intuitive explanation of why this works. Let's go back to our 5 people example. Our 5 people and 2 positions we need to fill. So, if we're choosing 2 of these people to fill up these 2 positions, that's the same as not choosing these 3 people. So, each time we choose 2 people, we are actively not choosing 3 people. And so conceptually, choosing 2 people is the same as not choosing, I'll represent that like this, 3 people. So 5 choose 2 is equal to 5 choose 3. And more broadly, n choose R is equal to n choose n minus R. Another important thing Pascal's triangle allows us to do is it allows us to figure out all the different ways we can choose from a set of objects. Let's say we have 5 different books. Or for the sake of shaking things up, let's make it 4 different books. And let's say your friend has these 4 books and he's telling you that you can take any one of the books, you can take none of the books, you can take one of the books, 2, 3, 4. So all the different ways you can take from the books is you can take 0 of them, you can take 1 of them, you can take 2 of them, 3 of them, 4 of them. You'll notice that this corresponds to the n equals 4 row of Pascal's triangle. So if you've got a set of objects and you're instructed that you can choose any number of them, then the total number of ways you can do that is going to be the sum of the nth row of Pascal's triangle. The n equals n row of Pascal's triangle, that is. This is actually equal to 2 to the power of 4. Why is that? Well, if I'm looking at this first book, I have 2 different options. I can either take it or I can leave it. So 2. This next one, I similarly have 2 ways, 2 options with this book. And this one, also 2. And this one, also 2. So the total number of ways I can either take or leave those 4 books is going to be equal to 2 times 2 times 2 times 2. 2 to the 4. So if I have n books, then I have 2 to the n ways of taking those books, which is equal to n choose 0 plus n choose 1 plus all the way up to n choose n. Okay? Let's say I have to choose at least 1 book. Then I can just write that as all the different ways I can choose those books and subtract where I don't take any books. This gives me the number of books I can choose given that I've taken at least 1 book. Okay, let's move on to the binomial theorem. Okay, the binomial theorem. Oh. What the binomial theorem allows us to do is it allows us to compute the sum of 2 numbers raised to really high powers, or even really small powers. Any power, that is. So let's say if you've already dealt with quadratics, you would know that x plus y squared is equal to x plus y, and we multiply the x's, and these ones, and these ones, and these ones, add those all together, and we get x squared plus 2xy plus y squared. If you don't know how to do this, don't worry. It's not entirely important to knowing the binomial expansion. So, let's say we have our Pascal's triangle over here. And I'll label this with the rows so we know. This is my n equals 0 row, so 0 choose 0. 1 choose 0, 1 choose 1. 2 choose 0, 2 choose 1, 2 choose 2. N equals 3, n equals 4, and so on and so forth. Okay, let's say we have x plus y to the 3. That we can write as x plus y multiplied by x plus y multiplied by x plus y. So this first one, this first term in our expansion, let's say we want to multiply all the x's. We have 3 different places we have x's. And so, if we want to multiply that, we have 3 different places we can choose an x from, and we want to choose 3 of those x's. So we have x cubed. Similarly, we could refer to that as not choosing any of the y's. We have 3 y's to choose from, we don't choose any of them, and so we get this. The next one, we are trying to choose 2 of the 3 x's. 3 choose 2, and we have x times x squared. The other one must be a y. Oh, why is that turned over? Plus 3 choose 1, x squared y. The next one, we choose 1x, and so we must choose 2 y's. The last one, we choose 0 x's, which is equivalent to 3 y's. Okay? If you look at these coefficients, you can see they correspond to the n equals 3 row of Pascal's triangle. So my coefficients for the expansion of x plus y cubed is equal to x cubed plus 3x squared y plus 3xy squared plus y cubed. If we have, for example, here, x plus 3 all cubed, that's going to be equal to 1 x cubed plus 3x squared times 3 plus 3x 3 squared plus 3 cubed. I will leave x plus y to the 6 and 2x plus 1 to the 4 for you to do. If you want to check your answer is correct, you can put it through ChatGPT, or if you want to, you can leave it in the comments and I can check and make sure your answer's right. Okay, so that is everything from combinations. We looked at the intuitive definition of what a combination was. We used the notation n choose r and n choose r, and showed that that's equal mathematically to n factorial over r factorial n minus r factorial. We then investigated Pascal's triangle and saw that it was actually a pyramid of combinations. We looked at the properties of Pascal's triangle and saw that it was symmetric and that each number was equal to the sum of the numbers immediately above. Then we had a look at the binomial theorem, and we were able to expand binomials raised to high powers of n raised to any power of n. So that's all those 3 points, and that's combinations done.
Hey guys, I hope you enjoyed that video and it was informative and it helped you. I just wanted to let you know that I'll be posting more regularly starting from next week. You should expect videos from me at 7 a.m. on Tuesdays, Thursdays, and Saturdays. And so make sure you subscribe to make sure that you're up to date with those videos when they get released. And as always, remember to comment if you have any questions or if I've missed anything, and I'll upload supplementary content. I hope you're staying healthy, that you're taking care of yourself, and that your studies aren't stressing you out too much, because I know waste can be a stressful time. Thanks, guys.